gonna speak about epilepsy disease and early diagnosis of epilepsy with the help of analysis and processing of MRI images and brain signals. And with the speakers, I, Elyas Irankhah, and my dear author is Imam Bagheri. So, in the next slide, please.
We can't hear your voice. I think you are on mute. So please unmute and then continue with your session. Please do.
Okay.
Yeah,
you hear me now?
Yes, perfect.
Okay. So we are gonna talk about seizure and what is the definition of seizure? You know, a seizure is a sudden, uncontrolled electrical disturbance in the brain. It can cause changes in your behavior, movements, or feeling. Actually, if you have two or more seizures or a tendency to have recurrent seizure, maybe you have epilepsy. There are many types of seizures which range in severity. Seizures type vary by where and how they, I think, begin in the brain. Most seizures last from 30 seconds to 2 minutes. No, yeah. And seizures that last longer than 5 minutes, it's a medical emergency. So in this slide, you can see the importance of science and the concepts of a seizure. For example, confusion, error, sudden falls, or uncontrollable jerking movements, strange sensation and emotions, and lots of conscious or awareness. So, epilepsy, in generally, I think epilepsy is caused by the sudden transmission of a large number neural message in the brain. To the brain signals or EEG, CT scan, PET scan, and MRI image diagnosis diseases, and methods such as surgery, medication, and electrode implants are used to treat the disease. But there is one important truth about it's that the origin of epilepsy is still unknown, as mentioned before. In order to diagnose epilepsy early, a combination of image processing and brain signal analysis can be helpful and beneficial. There is an important question about what does an EEG test do? In general, an electroencephalogram EEG records activity in the brain. Your brain constantly produces tiny electrical signals. During the EEG test, small sensors called electrodes are placed on your scalp. The electrodes are connected by wires to an EEG recorder. Electrodes are attached using a special paste glue. After the after the electrodes are removed, you may still have a lot of glue in your hair. And hair conditioner can help to remove the glue afterwards. And they only pick up the electrical signals. They don't interfere with your brain, and they don't cause you any pain. So the next question, what information does an EEG test give? Actually, an EEG test gives information about the electrical activity that is happening in your brain at the time the test is carried out. Many people with epilepsy only have unusual electrical activity in their brain when they are having a seizure. The rest of the time in brain activity may be entirely normal. So if your EEG test doesn't show any unusual activity, it only means that there is no epileptic activity in your brain at the time the test is being done. This doesn't prove that you don't have abnormal activity in your brain at others, and it doesn't exclude you having epilepsy. People with some type of epilepsy have unusual electrical activity in their brain even when they are not having a seizure. When they have an EEG test, the results can show certain brainwave patterns that doctors recognize. This information, I think, is very so helpful for doctors, specifically for doctors when they are making a diagnosis. About seizure, will an EEG test cause to have a seizure? It's a really important question. A seizure is a sudden uncontrolled and disturbance in the brain can cause a change in your behavior, movements, or feeling, and level of consciousness. If you have 2 or more seizures or a tendency to have recurrent seizures, you have epilepsy, and that's a risk. That's a risk of EEG test and flashlighting and breathing issue, and medical professional monitor. I think this could be caused by other medical condition problems or with their vision or brain damage. And the next slide, please. Neural network is really important to processing or signal or image, not matter, but it's really important because a neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. And in this sense, neural networks refer to system of neurons, either organic or artificial in nature. Neural network can adapt to changing input so that network generates the best possible result without needing to regarding to output certain. So after this slide, my dear co-author Iman is here, and he will be continued this presentation. And thank you so much.
Okay, thank you for dedicating the time, and I really say warm hello to the professors. So regarding the methods in diagnosis of the epilepsy, we're performing a kind of optimal processing of the EEG, optimal EEG brain signals, that it's a kind of combination between the image processing on the MRI and the signal processing on EEG signal, electroencephalogram signals. What we're going to perform is a combination of image processing and signal processing using the LMAN, a neural network for signal processing, of course, and the multi-layer perceptron neural network for image processing. And of course, the combination of calculating the accuracy after that, given in the details and elaboration in the exercise. Let me see. Okay. Comparing the EEG signals in the time domain, we have the most important thing that we can say about the voltage and the range of the voltage. Now coming back, please. Yes, voltage ranges and samples of the EEG are available here. That the range of the voltage is in millivolts from at maximum minus 100 or maybe a little bit less than that, and at maximum, I mean in a negative and a positive side, we have 100 millivolts. And the normal person, comparing to a mild person experiencing epilepsy and a person who experiencing a kind of severe epilepsy, is given here, as you see in the photos, to the left side and the right side and the down side. So if we go to the next slide, we're focusing on, please next slide, if it is. Let me just see if I can do it myself. Yeah, we're just comparing the waveforms that create an EEG signal. One of these waveforms that are really important, frequency from 0.5 to 4 hertz, and then the frequency of the theta that we have it here, which ranges, I mean, a little bit higher than delta and ranges from 4 hertz to at maximum 7 to 8 hertz. And then we have the alpha. Still, the amplitude of these signals are going to change, of course, but in terms of frequency, the alpha and beta are the frequencies that are ranging from 8 to 13 and 13 to 30 respectively. And of course, the last but not the least important thing is about the gamma, which has the higher frequencies. I mean, the frequencies over 30 hertz. So let me see if I can continue in the next slide. So we have it that EEG signals in the frequency domain compared with the time domain, that we see that in the left and the top photo that we have a normal EEG in the frequency domain. All of these figures are in the frequency domain. And the fact about these figures is that when we go through the left side, we have the lower frequency and the frequencies that are near to the DC. Then we go to the right side. As we go through the right side, for example, 10, 20, 30, 40, 50, and so on, we have higher frequencies. So still we see that the comparing the normal and the mild and the severe EEG, we can mention that we can see that there are differences between these things, but in a mild EEG we have the lower values. So going to the next slide, I'm going to provide some information regarding filters that we can perform, and of course I'm explaining this slide, and after that I will explain through the filters and how these effects on EEG. Imagine that we have a high-pass filter or HPF. Assuming that this is an ideal HPF, we have something that from a cutoff frequency, it can actually remove from before that, and it can allow to pass the frequencies upper than that, I mean after that. So the same story is for the low pass filter, in which the frequency, actually the kind of filter on the frequency is trying to pass the frequencies before the omega C, which is the frequency here. And then we have the band pass filter, which allows to range from the frequency of low and the cutoff frequency of the high, and something between that. There's of course another filter that in which we are going to describe in the next slides, that some of them are called band stop filters. So, if we go to the next slide, I can mention that the EEG signals frequency bands after the filtering each band, as we can see them here and indicated again as the aforesaid thing I pinpointed, we have the delta, theta, alpha, beta, and gamma in terms of increasing the frequency. And then we have these waves that we can see that these are the signals, EEG signals that are performed for every actually band of frequency, that each one of them are filtered. I mean, for example, achieving the top right figure that we have it here, in which we have the signal for the theta, not, the left one is the delta and the right side is the theta. So we're going to have a kind of filter that try to pass the frequencies between 4 to 8 hertz. That's what it performs, and the rest for the other figures. So going to the next slide. You're mentioning that our methods in diagnosis the epilepsy, of course, before introducing this method and going deep into the details, there's one thing that I have to focus, which is the band stop filter that is remaining from the previous slides, yeah? And this band stop filter that you have it in here, and you see it in this slide, is a kind of filter that doesn't, this does not allow some frequencies to pass. I mean, very, very specific frequencies. And one of the specific ones of these banded stop filters is the notch filter that can actually remove the frequency of 50 hertz or maybe 60 hertz of the electrical outlet, I mean the power. And when it comes to speaking about the diagnosis of epilepsy and our methods, we're going to describe the first method, the segmentation. Dividing signal to 2 or more, even more segments is something that we can perform in the segmentation. And the aim is, of course, to perform something feasible and easier in terms of processing, signal processing. We are actually here using the MATLAB curve fitting toolbox that we have the equation here in the downside, in the right side. That you see it in corner, the f of x is equal to p1 of x plus p2. These are the coefficients that we have it here. So going to the next slide, please. We can see that going deep in details in the formula and the calculated values for the person who is experiencing a normal EEG, comparing to a person that has a kind of mild epilepsy and the severe case. In terms of epilepsy, we can see that these are the some of the 3 linear model polynomial that we actually achieved in this research. And comparing to the figures, the most important thing and significant feature that I wanted to dedicate here is the fact that as the more chaotic the signal is, the person is in normal thing. I mean, this is not experiencing epilepsy or seizure or something like that. I mean, the family of seizure, which is epilepsy. As the signal is very chaotic, it is a kind of normal signal, a normal EEG signal. But when it comes to talking about, it has some patterns, the seizures is going to happen. So next slide, please. And the segmentation in the diagnosis of epilepsy regarding the previous equation that we performed as comparing to the normal cases and the mild and the severe cases, we can see that these are the scattering. These scattering dots are the signals that we receive and the amplitude of these signals regarding the points that we achieve them in terms of time. And we see that the patterns actually increase and actually is going to get longer and longer in terms of distance that these dots are going to happen, which definitely showing that the person is in the case of severe epilepsy. So going to the next slide. What we perform is that, yes, please, next slide. The statistical features, we're going to describe a little bit about the central features, which include the mean arithmetic, including mean arithmetic and geometric mean and the harmonic mean, as well as the median, the middle element, I mean, between the, the received signals, and the mode which shows the maximum repetition of the signals. And among the dispersion features, the most important thing that they're really important here and significant, which are the variance and the standard deviation, showing the fact that how different is a value of a signal that we receive and a point that the amplitude received in terms of distance to the median. I mean, to exactly the mean, the difference between every element to the mean. So the range is also defining the maximum element minus to the minimum element, and then we get going to the shape features that are the higher moments, such as skewness or kurtosis. So when we perform these statistical features, these are really important for us. So please going to the next slide. And then we're going to describe a little bit about the conformity in statistical features, including demonstration of similarity in the frequency domain. So it means that when we are calculating conformity using the formula given that is in terms of frequency, that you see this is a kind of positive value and it is also even, indicating the fact that how similar is these values together. And the horizontal value is considered for the frequency, and the vertical value actually is called for the similarity. So using the phase difference, it can be very useful for the phase difference measurement, I mean the conformity, And going back again to our research and the data that we received through that, these figures are performed using MATLAB. And you see that the top one is for the normal person, the middle one for the mild person experiencing epilepsy, and the last but not the least important is the severe epilepsy. So going to the next slide, please. These statistical features among normal and mild and severe cases that I mentioned are interpreted here that you see in 3D. So again, one of the most important things that I would like to show you here is that this blue one is of course showing the delta, and the red one is showing the theta and alpha and beta and gamma. So what matters here is that in the last figure, we see that the delta has a very high actually amplitude, which is really important. And coming back to a normal person, we see that everything is in normal, not very differentiating or not very different. I mean, in terms of the value that we have, they are not very scattered. So this is also indicating our previous mentioning. So going to the next slide, please. So this is another important feature that we're going to describe here, the return map. So the aim of return map is to find a hitting point, of course, showing the similarity to the current, previous, and the next samples of the EEG. And using the return map, we can actually have some shape features such as how periodic is the signal. Is it, for example, non-periodic or semi-periodic or even chaotic? And parameters like trajectory of the system in state space, and of course, cruising points that are important, of course, indicating that how the system works by analyzing the return map. As you see on the right side, we have two figures that one of them is indicating actually a visualization on a line between a normal and mild and the severe according to our data that we performed in our research. The 3D visualization interpretation shows that the samples on the line and the longer distance is, the less chances of epilepsy is going to happen. And centralized and circularized in the phase figure that we have in 3D in the right and the downside, we have the blue actually curves that we see that they're circularizing and going to the center. Deep in the details of the centers, as we go deep into the centers, we have more similarities found in the return map, which increase the chances of epilepsy in the people. In the patients, I mean. So going to the next slide, please. We see that, so I'm still waiting for the next slide. Let me see if I can, so among this part, we finished actually the signal processing, and then we're a little bit focusing on image processing, and then coming back to compare both of them. So regarding the image processing of MRI images, we have the binarization of the image that can create a kind of threshold in the image that the gray values will be converted to 0 and 1 and to black and I mean very light, very white. And then we have the noise reduction filter that can be very useful. As you see, the right photo has some noises. Noises are defined as something that we sprinkle like a kind of a sprinkle, coming back please, yeah. Sprinkle some dots on the image. And then, okay, so it sounds like we're out of time, so we're focusing on the image processing and the, okay. Okay, thank you. So the edge detection, the edge and the light intensifier filters indicating that makes the photo, I mean, brighter in terms of filtering. And then coming back to the image processing and the multi-layer perceptron neural network that we performed, then again, we're coming back to the central features like mean arithmetic, geometric, harmonic that I mentioned before, and the mean and the middle elements that we mentioned, and the dispersion features. So going to the next slide, please. The element and the multi-layer perceptron that we performed for the EEG signal processing and the MRI image processing for MRI images, we're using neural network architectures. So generally deep inside the neural network, we have generally 2 layers, including a recurrent layer providing feedback from the first layer output. So we have feedback from the layer output. and including some hidden layers between them. And the recurrent structure that we have, the definition of the recurrent structure indicating and demonstrating the fact that we're updating the weights. So weights in the neural networks are updated after getting feedback from them. So based on the number of neurons, there are features in the hidden layer. So as we increase the number of neurons, we increase the features in our layer. So in the final results and conclusion, epilepsy sudden, it means, as a definition, it means sudden transmission of huge number of neural messages that are coming to the brain. And the most important truth about it is the fact that its originality is something that we can confront as an obscure and something that is unknown phenomena. And brain signal analysis using the Iman neural network is performed. And then in the image processing part of our research, we performed on the MRI images using the multi-layer perceptor neural network. And the statistical features that used here are central, I mean, in terms of central or mean, here arithmetic mean, mode, and median. But the one that has the more effect here is the mode in the statistical features regarding the signal processing of the signal processing of these signals. And the final result and conclusion regarding the statistical features and depression among the normal, mid, and severe cases, we know that the range and standard deviation variance, of course, are really important. And the least values, which is really important for us, is the gamma here. I mean, in terms of the gamma frequencies, indicating more variance and other statistical features dispersion. Calculating the accuracy, we used the table that true, positive, negative, false, positive, and negative, and positive, yeah. And with calculating the using the accuracy for the Iman neural network and the extracted features, the statistical features related to the EEG are really important for us, and it can actually provide these features, the nonlinear features for phase map. Phase map is also another name for the return map. So we have the statistical features related to the MRI images as well, and regarding the calculation of the accuracy results among these three groups of people, the categories, I mean the classes of people. We have again normal and mild people. We compared them normal and mild, normal and severe, and mild and severe people. So going to the next slides, we're giving some our final results in a table that indicating that when we are only using the signal and signal processing technique, and we're using Iman neural network, we have the normal and mild people, I mean, not experiencing epilepsy, that shows the accuracy of 73.8%. And comparing them to the normal and severe, we have 78.2, and mild and severe 72.9. We will discuss about the interpretation about these values. And then when we have the image, we have 81, 84, and then the other results. That the most important thing is that when we are using at the same time signal and image, it doesn't mean that we are using both image and signal. We are receiving the fact that whether a person is experiencing epilepsy or not. We know that, for example, someone has epilepsy by the input signals that we receive and the input values that we have. We see that when we are using signal and image at the same time, and I mean, it's kind of or between them, we have a better results that we have on that table. Thank you very much for dedicating the time, and I'm waiting for any questions.
Thank you. Yeah, thank you so much for both of you. So I request other speakers have any questions to Iman and Elyas, they can ask now.
I have a couple of questions and an idea. So let me start with what I think is less important. That's your statistical analysis, because at the end of the day, it's the big idea that's more important than the stats. So your analysis was based on FFT?
No, it was not based on FFT. It has frequency, but it is not fast Fourier transform. Definitely not indicating the fast Fourier transform that you're mentioning right now.
No, because you didn't. And if you did use
talking about FFT, I know.
I would have given you a whole thing about Hilbert transforms, but I don't want to get into that. The second thing is you have a model. It's a two-layer model.
It's a kind of, no, it has more than, I mean, the most important thing is the first layer and the last layer, but there are some hidden layers between.
Yeah, because the brain is more than that.
Yeah.
The third thing, and these are the technical questions, then I have something which is a suggestion on top of that. The third thing is your stats are based on median mode, excuse me, median mode and
Range, you mean? Yeah.
right.
Yeah, mean and median mode. Yeah.
What did you do about
mode? As a definition of the mode, yeah, I'm going to answer. Is your question finished?
No, I was going to say, what are you doing about the homogeneity of variance? Is it homogeneous? Is it heterogeneous? In other words, these are multiple factors in there. So is that really, is descriptive statistics the best way of getting into it?
Yeah, of course, units, yeah, and yeah, of course, these are really important to be noticed, yeah, and to be considered, of course. What we performed regarding the fact that why we are using the mode that has the most significant effect here is just by the definition of the mode. So what is the meaning of mode? You know, when we compare it back to the, for example, the median means to select the middle signal. When it comes to mode, it means the free. So what is important in the epilepsy, what matters to us is how it happens, I mean, in terms of signals, and how scattering is in terms of line or phase on the phase map, that how centralized are them. So what matters, the most important feature here is mode, and the repetition of these things when they are repeated too often and they are centralized, or maybe in a line that are just I mean, in terms of dots that we receive in terms of signals. It shows that we have epilepsy, but as they scattered and they are chaotic, it shows that the person that is experiencing not epilepsy, or maybe very mild epilepsy. That's why we perform this.
Now my point, which is, now we've solved the statistical issues. It was a study done in 1974. It's pretty well known. It was a clinical study, and this is possible for you to directly apply it to this. You should look at it. It came out in the Journal of Electrophysiology, Electroencephalography and Clinical Neurophysiology. The author, senior author of the paper, was a guy named M.B. Sterman, S-T-E-R-M-A-N.
Once again.
Sterman, S-T-E-R-M-A-N, M.B. And Barry is his name. And the journal was the commonly called the EEG journal, but it's the Journal of Clinical Electrophysiology and Clinical Neurophysiology.
Yeah, I got it. Yeah.
Okay. What he did was he was going after a patient with intractable epilepsy. So this lady had 350 or so seizures, grand mal seizures per month. And besides that, they were all of it was uncontrolled by medication. And so she was in a constant state of status epilepticus, which is you're going to die. So what he did was he put her, he recorded EEG, and the EEG output was attached to a row of bulbs. And the object of the exercise was for this patient to turn on the bulbs in sequence, in seriatim. And her task,
kind of from like BCI, you mean?
No, it wasn't. It's not BCI because it's completely external. It's on surface electrodes.
Oh, yeah, I see.
And the only way that the light bulb would go on was any time that there appeared in the EEG normal activity, non-epileptic activity at any point. It took her a while, but what happened was in the space of, I don't know, 2-3 weeks or something like that, this lady was able to turn on all the light bulbs. And what happened was she disappeared the status epilepsy. Then her number of seizures went from, I don't know, 350 or so to maybe 20 a month, and those were in turn controlled by medication. What I'm suggesting here is that what you've done actually is a potential marker for the treatment of epilepsy, because you've identified, this is the cognitive piece. The cognitive piece is you're getting this lady to make a decision about when to turn on the light. And that decision is based on the absence of epileptic activity, not the presence of it. So now that you know what epileptic activity is, you now have a binary algorithm, which is it there, is it not? And who cares from which leads? Your object is to make a frontal lobe decision to turn it off.
Yeah, exactly. And we're performing accuracy about, and which is not just limited to 0 and 1. I mean, the binary, just to dedicating the fact that whether someone has epilepsy or not, we're calculating and predicting and anticipating the fact that how prone he is to have epilepsy. That's what we perform.
This is the next step. What you've got in your hands, I believe, at least as I understood it,
Thank you very much.
is the decision of you don't have it. That's more important than you have it.
Yeah, exactly. Yeah,
Because that allows you to.
because that person could be clarified about it, that okay, thanks God that I don't have epilepsy, and I don't have any chance in the future that I become, I don't know, prone to epilepsy or experiencing this. This is what we actually, our team actually performed.
It's a potential great contribution to
Thank
do
you.
that.
Thank you very much. Thank you so much. Is there any other question that you would like to ask, or any other members that would like to ask?
Any more questions? Okay, that's it. Thank you so much for both of you, Alice and Iman.